really proud to have our partner Intel here. Vijay Bandari is with us, and David Vike is back for the second time. He's the only two-time Spotlight Stage presenter, so welcome back, David, and I will turn it over to you two gentlemen to take people through the Intel Inside. I had to use that, right? So.
Thank you, thank you, thank you. Hope you can hear me, but Intel Inside, who doesn't know Intel Inside? Who doesn't know the jingle, ding dong dong, right? So, of course, Intel saga goes on, and we actually technologically make progresses to make sure that our customers are experiencing the technology at a transparent way. This is one of the attempts to reposition our technologies and product line for AI and analytics. Alongside me right now, we have David, and our partnership goes ages, like last 25 years. We have co-engineering teams working with each other. All the product lines and innovations that SAS does, our engineering teams work and make sure that it works best on Intel architecture. Some of the numbers that you see here are from the latest generation of equipment that are being used by SAS with the increased speeds and throughput that we can see. And this, as I'm saying, AI everywhere is the mantra that we are actually following. Some of the product lines that we have all the way from edge to the cloud, Arc, Core at the edge, Xeon, Arc, Core, and Gaudi are a product line that actually are applicable. And our mantra is to look at AI as one unified platform that can work on Intel product line. And with the innovations that we are adding progressively, that makes it easier for making this unified architecture work for the AI. So Xeon 6 is the latest generation of CPU that we have introduced into the market late last year. And actually, OEMs are rolling out product line based on Xeon 6, and where CSP is progressively bringing our instances based on Xeon 6. Some of the optimizations that we brought in for that we are trying progressively building is for AI and HPC and database workloads, and this is all possible because of the architectural improvements, the core density, increased memory lanes, and memory options. Like example, MRDIMMs that are now possible, making some additional workloads and efficiencies possible, like what you see on this slide.
Yeah, and Vijay already mentioned that SAS has a deep collaboration with Intel, and anytime they come out with a new hardware generation, we run it through our paces because the SAS workloads are kind of unique, as you know, right? We are not typical of the mill. So this is kind of a look at comparing AMX, which we're going to be diving deeper into what that actually means and how it compares across different algorithm sets that you are probably running today within your workloads within SAS. And you can see that on average, we see a gigantic uplift over the traditional non-AMX workloads, which can help speed up your iteration times, get more tests and requirements through as you're scaling up. And the cool thing to me is this doesn't just scale across the same data set, right? We make sure to test it across a varied set of algorithms, but also data set behind that of varying sizes and structures to make sure we represent the type of workloads you are running in the field with the SAS software. So I think this is incredible numbers that we are seeing across the board, and almost 1.7 times uplift that we get here just by enabling an additional feature.
Thank you, David. So the work doesn't stop with this table here. We continuously work on some of the evolving patterns of workloads. We do test out combinedly, and we actually educate each other about the patterns that we are working and then how best we can optimize our architecture and software together to provide best performance on our platform. It's a AI, as I was mentioning, edge to the cloud. I think this slide actually takes data center and the cloud into the consideration. AI, classical AI and ML, and emerging workloads like generative AI. If you actually put them in kind of three pillars here, like classic AI, ML workloads, small generative AI models, it is not a hard and fast rule of 20 billion parameters is that cutoff points. But based on your workload, the SLAs that you're trying to drive, and the concurrency that you're trying to serve, our advice to the market is anything less than 20 billion parameter models, inferencing and fine-tuning is a fair game on CPU. And as the concurrencies increase, model size increase, you might require a accelerator. And Intel has an accelerator that I'll actually talk about called Gaudi, and we have third generation Gaudi 3, where we can apply the right product to the right. AI is not a monolithic one workload that you should look at. You should look at the life cycle of the AI, all the way from pre-training, training, fine-tuning, and inferencing. And its distinct requirements for each stages of this life cycle is different. You should actually look at each of those stages as a different workload, and then you make the right choices of the product line that Intel offers to get the best TCO and performance out of the platform choices that you're making. Advanced matrix extension is a newer accelerator that we have introduced in Xeon line of CPUs. From the fourth generation, right now the latest is the Xeon 6, is the sixth generation. And most of the OEMs have product lines with different pricing that you can choose anywhere. When you're making those choices, make sure that you're above Xeon 6. Our advice is to go for Xeon 4. Our advice for you to choose Xeon 6, even though if you play a delta of certain percentage, performance gains will easily nullify and provide better TCO. So Xeon 6 actually, and fourth onwards to the 6th, we have introduced this AMX accelerator. AMX accelerator is an accelerator added on top on the core itself. For example, you have a two-socket system with 512 cores on it. That means 512 accelerators are working for you. And this accelerator is, we are adding matrix multiplication engine, basically having a special register to store your data in an array format or a matrix format, and then a newer instruction to multiply those array or the matrix in such a way that you're not processing data element by element, you're actually taking a table of data and multiplying rows with the columns. That's how you get the maximum throughput. And also, the deep learning workloads do not require complex calculations. It's multiplication and addition. I think by having this special instruction and registers, we are able to see anywhere from 5x to 10x performance gains for DL workloads. By having AVX 512 and AMX on the chip as options for a scheduler to dispatch the threads to, the frameworks are able to do self-discovery on the platform, and the scheduler is able to direct the threads to the appropriate instruction, AVX 512 through AMX side by side, in a DL or ML workload. So I tried to explain where it is, but basically the AMX is not a accelerator sitting outside the core adjacent to the socket. It is a part of the core itself. You can see the traditional optimized accelerator sitting right there. That means every core has an accelerator, has numerous cores and threads that you use, either in the form of a bare metal or as a vCPU in a virtualized environment. This is the accelerator is getting used. And till fourth and fifth generation, we had BF16 and int8 as the qualifying data types. We have introduced FP16 as a qualifying data type with our latest generation. And between our generation, there has been progression in AMX. There has been an increase in the frequency of the AMX accelerator itself. That means Xeon 6 will provide you best performance possible. And these are some of the numbers. If you see here, I talked about AVX 512 and AMX with Tumo. So the first bar on the chart, it shows you AVX 512 with FP32 versus AMX quantized to BF16 or FP16. About 16x performance that we have seen in our labs. And some of the customer workloads specifically have proven anywhere from 5 to 16x performance when you're taking this approach. AVX 512 with int8 quantization versus AMX with int8 quantization. You can see the difference in the workload performances there. And majority of the things that you need to do to take advantage of this is nothing. As long as you're using most popular frameworks like PyTorch, TensorFlow, Onyx, some of the XGBoost, scikit-learn. These are the frameworks which optimizations Intel works on and upstreams its code in such a way that wherever and whenever you're using Intel architecture, these frameworks have the self-discovery capability, and scheduler is able to make the choices to give the maximum performance out of your systems. OpenVINO is a tool that Intel provides for free that actually allows for you to develop your models on one system, like all the way in a Xeon-based or GPU-based model that if you have developed, and OpenVINO actually makes you the migration of the model or the moving the model easy, that you can actually develop once and deploy in many places. If you're actually trying to push the inference to the edge, the same model with int8 quantization, which was trained on FP16 in cloud or on-prem, is a fair game where you're trying to solve inference, maybe 30-40% of inference happening on the edge. You're leveraging your data center or cloud to do pooled consolidated second model refining and redeployment. That is a possible scenario that you can work on. Little more on the software infrastructure here. So we have Intel has one API, one DNN, one CCL, one MKL, and analytic libraries, some of the data analytic libraries. These are all transparent to you. If you are deep into development and if you're able to touch some of the underlying infrastructure, these are all open source. It's available for you to use. Some of this work, we actually work with our vendors. Like, for example, if you're working with Microsoft or AWS or GCP, we are actually working with them and make sure that the technology like AMX and TDX are exposed to you and usable transparently in such a way that all these optimizations are actually being used when AMX is exposed. And if you are doing C++ programming, having your own frameworks to work on, some of these libraries and tooling is available for you to use. I think one other way to actually test out all these things that I talked about, we have Intel Tiber Developer Cloud. It is almost like a playground for you to come and test our technology. As a service or as a bare metal, there are multiple options that you can use. And the Tiber Cloud, and then there are some of the models that we actually continuously publish, pre-optimized for you to consume. That means you can pick the model from Hugging Face/Intel, all the way from edge and core-based models to a large-scale models, all the way from 7 million to 670 billion parameter models that are pre-optimized and kept for you to consume. So when I was talking about some of the deployability of LLMs, their performance, what you are actually looking for is, in general, 100 milliseconds is a humanly perceivable latency, but it is less than or more. If it is more than 100 milliseconds, probably you cannot read you cannot read fast enough, which is if it is producing less than 100 milliseconds. It actually matches the human reading speed. If it is the response time is beyond 100 milliseconds, you might feel that the response time is slower than what you can read. But some of the numbers that we are showing, first token latency, and the token latencies that you're seeing here is 200 milliseconds, 140 milliseconds, versus 3 seconds to begin with, or 5 seconds to begin with. The first token, when you submit your prompt, by the time it responds, probably it might take about 3 seconds. And multiple choices that we are seeing, like the token latencies that I'm talking about here are the ones that you're actually trying to decide on as an SLA. Based on the SLAs and the size of the model, you can actually deploy those models on Xeon 6 with AMX accelerator. In our guidance, for example, is 20 billion or less. You can deploy on Xeon with about 200, up to 200 users or 300 users. If your model is being used by, let's say, 10,000 users, in those cases, you have to go for an accelerator like GPU. In our case, we have a GPU called Gaudi, especially built for deep learning. So this is some of the things that we have validated in our labs that you can see. So just to give one more look at what are the options available, the CPUs without AMX versus AMX. This makes our CPU world's best CPU, and some of the performance metrics that you can see here for the most popular models that you can encounter in the market. I think I claimed world best CPU a slide before, but actually this actually makes it possible for you to see the technology makes the difference, the choices that you can make based on the workloads that you might have to execute for. DLRM is one of the workloads that, like ad serving, in-game experience, some of those things are not truly the large generative AI. It might fall into ResNet, and BERT large might fall into your classical AI and ML workloads. These are some of the LLM workloads that you can see in the background. So I just mentioned about trusted domain extension, or TDX. So this is another newer technology that we have introduced since Xeon 4, the fourth generation of Xeon onwards. Xeon 6 also has a TDX. This actually allows you to do confidential compute as a protection mechanism for you to do AI responsibly and protect your own data, your own model from hacking. So basically, your data in memory is protected by silicon-based encryption. In those cases, your attack surface, I would say, has decreased by about 10x when you're doing software-based implementation versus TDX-based implementations. This is available on all bare metals that you can buy from OEMs. Some of these, the CSPs have specialized confidential compute instances that you can actually realize today. So what is TDX? So we had a confidential compute technology that has been used in the market for a long time. Enclaves that you can create where data in memory is protected, and each enclave was in a way that you could realize a part of your VM to be enclave. But in this, with TDX, we have increased the periphery of the enclave to include whole VM. That means you can protect your data, you can protect your model, your interactions are all encrypted. Even if somebody has access to the memory, they will see gibberish, and CPU does not need to unencrypt and process the data. It can figure out and process the data on an encrypted data bytes. So Xeon 6 processor, in a way, what we are saying is traditional data centers, you might have older servers that are actually aging out, could be all the way from Broadwell, Ice Lake. There is ways for you to consolidate. There is we actually paid attention to increased, reduced power consumption. If you are working under a certain power envelope, there are optimizations that you can put in. You can reduce your server between anyway all the way from 5x to 17x based on the workload that you're running. Reduction in the server count, reduction in the cost in terms of TCOs compared to the traditional deployments that we have. Gaudi is, I do not have too much time to spend here. This is a specialized, in colloquial terms, it's a GPU for deep learning, but it's an ASIC specially built for deep learning with tensor cores and matrix cores and HBM memory and increased number of Ethernet bandwidth that actually you can realize. And the TCO, some of the software, I'll skip this slide. These are the pre-validated models that you can readily deploy as of now. Some of the frameworks that it can work on. And this is a kind of a chart. You can actually scan the QR code. This is based on one of the customer experience where H100 and H200, the most used GPUs, and how there is a TCO that you can achieve when you're using Gaudi 3 as a substitute for the GPUs that you popularly use.
As a wrap-up, if you allow me, as a wrap-up, I know we are close to time here. On Tuesday, our people that participated in the SAS Hackathon Bootcamp actually had the chance to build an agent like Brian showed on main stage yesterday, Diana showed on stage today. And they built actually their own agents here powered by LLMs running on the Intel Gaudi platform to just quickly iterate. And what they did there was build their own itinerary for tonight to choose the rides that best suit them, predict which ride times they will have, right? And they got their own personalized schedule. And all of that was possible because we had such powerful hardware in the background, so all of them could iterate really, really quickly in parallel. So that's the kind of performance you can get out of this and combine it with these types of agentic systems.
So I think we ran out of time, but thank you for participating and listening to us.